This example is from the text Conceptual Dynamics. Specifically, this is example 5.6-10. The problem statement reads, a particle with a mass of 2 kilograms is confined to move along a vertical slot while being pushed by the rotating arm shown. The distance between the pivot and the slot is L equals 0.7 meters. Determine the force of the arm on the particle and the normal and friction forces of the slot on the particle when theta equals 30 degrees. The rod is rotating with angular velocity and acceleration of 0.5 radians per second and 1 radian per second squared respectively. The ball is made of brass and the slot is made of mild steel. Assume that the particle contacts only one side of the slot at any instant and does not roll, but slides. Reading the problem, we try to understand what's happening. We identify the information that's given and the information we wish to find. We're told the mass of the particle is 2 kilograms. We're told about the geometry. We're told what L is. We're told what theta is. We're told the angular velocity and angular acceleration. So theta dot and theta double dot. We're told that the ball is made of brass and the slot is made of mild steel, and that it doesn't roll, but it slides. So the fact that we have a ball that's sliding means that the frictional force will be kinetic friction, or that's how we'll model it. And so we need to know the coefficient of kinetic friction. If we look at Appendix C of the book, we can see what the friction is between relative surfaces of brass and mild steel. It turns out that the coefficient of kinetic friction is 0.44. We are then asked to find the force of the arm on the particle. So I'll go ahead and call that F. And then we're also told to find the normal and friction forces of the slot on the particle. So I'll call the N for the normal force and F sub F for the friction force. Another piece of information that we're given, so while we're not given explicitly what the velocity or the acceleration of the ball is, we do know that it's confined to move in this slot. So we know that V and A are constrained to move vertically. So there we've read the problem, sort of understand what's going on. I'm going to go ahead and recopy this information to the next slide in order to give us some room to work. So this is the given information. We also know that L is 0.7 meters. Theta is 30 degrees. So here we can tell that this is a kinetics problem. We're asked to find forces, the forces that are in essence causing the particle to move. The only approach that we know for solving kinetics problems so far is what we'll call a Newtonian approach, using Newton's second law in particular, which is that the sum of the forces equals mass times acceleration. And so we wish to find these forces, but we don't directly know what the acceleration is. We're given a lot of information that could help us find the acceleration, but we're not told it explicitly. So the way we're going to do this problem is in two steps. First, we're going to find the acceleration. In order to help us with that, we need to define a coordinate system. Looking at this, there's sort of two coordinate systems that look feasible. So one would be to use rectangular coordinates or XY coordinates because the ball is moving in a straight line. In essence, it's moving in the Y direction. And we could do that using geometry to sort of make a right triangle here to define what the position of the particle is in XY coordinates, and then differentiating that to get the velocity and then subsequently the acceleration. Instead of using XY coordinates, we're going to go ahead and use polar coordinates. And the reason that we're going to use polar coordinates is because we're given information about how the particle is moving relative to sort of a fixed reference frame or a fixed origin. So this information here about how theta is changing is going to help us define this system in terms of polar coordinates. So looking at this, here's our origin. The radial direction is pointed away from the origin towards the particle. The transverse direction is perpendicular to that in the direction of increasing theta. And if we go back to our notes regarding acceleration in polar coordinates, we have these relationships. So the velocity in polar coordinates is equal to r dot in the radial direction plus r theta dot in the transverse direction. And then the acceleration has the form r double dot minus r theta dot squared in the radial direction plus r theta double dot plus 2r dot theta dot in the transverse direction. So ultimately, we want the acceleration. If we look at this, we are given information about theta dot, theta double dot. We can find r from geometry. So if I go ahead and sort of consider the right triangle that we have here, r is the hypotenuse. We know this leg of the right triangle, and we know that angle. And so since this is this adjacent side to the angle, we could use cosine. So cosine of 30 degrees is equal to adjacent over hypotenuse. So it's equal to L over R. If we want to solve for R, we have L on this side, which is 0.7 meters. We divide through by the cosine 30 degrees, and we get that our radius is approximately 0.81 meters at this instant. So we have a lot of information for solving for the acceleration, but we don't have enough. Specifically, we don't know r double dot, so we can't get the radial component, and we don't know r dot, so we can't get the transverse component. However, we can get r dot by looking at the velocities. Okay. So this is something that will look familiar from what we did earlier in the course when we were talking about kinematics of a particle. So what we're going to do is we're going to first analyze the velocity. And so if we look at this, we have enough information to find the transverse component. It's r times theta dot, where the radius is 0.81 meters approximately, and theta dot we're given to be 0.5 radians per second. And so if we punch that into our calculators, we get that the transverse component of the velocity is approximately 0.404 meters per second. Okay. And so while that doesn't give us r dot directly, what we can use is we can use the fact that we know the direction of the velocity. So we know that the velocity is straight up because it's constrained to move in that vertical slot. We don't know what the radial component is, but we know the direction of the radial component, and we know the direction and magnitude of the transverse component. So this is 0.404. Okay. These are at right angles to one another. This angle is theta. This angle is also theta. And so again, using geometry, we can solve for what it is we're trying to find. Ultimately, we're trying to find this side of the right triangle because we need r dot in order to find the acceleration. And so we know the adjacent side, we know the side adjacent to this angle. We want to find the side opposite that angle, and so we can use tangent. Tangent of 30 degrees is equal to opposite over adjacent, where we know what the adjacent is. So we can solve for V sub r. It's tangent of 30 times 0.404 meters per second. We type that into our calculator, and that works out to be approximately 0.233 meters per second. So that is our r dot. Once we have that, we can then move on to the acceleration, which is ultimately what we need in order to find those forces that we're asked to determine. So looking at what we have over here, we now have enough information to determine the transverse component of the acceleration. We know r, we know theta double dot, we know r dot, and we know theta dot. So plugging in, we have a radius of 0.81 meters. We have a theta double dot of 1 radian per second, plus 2r dot, which we just found over here. And then theta dot, which is given to be 0.5. If we punch that all into our calculator, that works out to be approximately 1.043 meters per second squared. Okay. And so that gives us one component of our acceleration, but we actually will need both components. We'll also need the radial component. And so the way that we'll find that is again to rely on the geometry. We know that the acceleration must be along this vertical line because the particle is constrained to move in that line. Okay, so it'll be vertical. The transverse component of the acceleration is positive in the positive transverse direction, equal to 1.043 approximately. In order to make this triangle work out, the radial component must also be in the positive direction, and that means that the acceleration is upward. This is again equal to theta. These are again at right angles to one another. And so using the same sort of tangent that we used, tangent of 30 degrees is equal to the side opposite, which is the radial component divided by the adjacent side, which is the transverse component of the acceleration. And then we can solve for the radial component. We have tangent of 30 degrees. We multiply the transverse component, which is 1.043 meters per second squared. Punch that into our calculators, and that works out to be approximately 0.60 meters per second squared. So that gives us the complete acceleration of the particle in polar coordinates. Once we have that, we can then go back to Newton's second law to actually find the forces. So we'll continue that on the next slide. So the second step is to find the forces, specifically these three forces. I've repeated everything that were given in the problem, as well as the accelerations that we just calculated. In order to set this up, in order to use Newton's second law, we need to draw a free body diagram of the particle. So I'll go ahead and draw that here. Recall that we're using a polar coordinate system with a radial component and a transverse component. If we look at this, the forces that are acting on the particle, one is its weight, which is straight down. One is the force of the bar pushing on the particle. So in essence, you can sort of think of that as the normal force of this arm pushing on the particle. So that force will be perpendicular or normal to the arm. And I'm calling that force F. Then there'll be a normal force of the slot pushing on the particle. We are told to assume that the particle or the ball only touches one side of the slot at any time. I'm going to sort of assume that the arm is pushing the particle into this side of the slot, and so the normal force is going to be perpendicular to that. It's going to be in the horizontal direction. And then we also have the frictional force. So the normal force is kind of like the force of the slot perpendicular to the slot, and the friction force is sort of like the force of the slot parallel to the slot. So this ball is sliding against this side of the wall, and so the friction force is going to push down, opposing the direction of its motion. So this completely defines all of the forces. This is still 30 degrees. And that's going to help us break the normal force into its radial and transverse components. You can sort of imagine that this normal force is broken into a radial and a transverse. Same thing with the weight and the friction force. It's going to be broken up into a transverse component and a radial component, where this angle is also 30 degrees. So once we have the free body diagram and understand what forces are acting on the particle and what their directions are, we can then go ahead and apply Newton's second law. Sum of the forces equals mass times acceleration, where this is a vector equation, and we're going to break it up into components. We're using polar coordinates. So we'll have the sum of the forces in the radial direction equals mass times acceleration in the radial direction. If we look at the radial direction, we have a component of the normal force in the positive radial direction. The component is the adjacent side in the right triangle, so we'll use n times cosine 30 degrees. The weight and the friction force also have components. They're in the negative radial direction. And if we look at this right triangle we've defined here, the radial component is the side opposite the 30 degrees, so we'll use sine. Same thing with the friction force. And that's equal to mass times acceleration. Friction force, the way that we're modeling it, we model it as normal force times the coefficient of kinetic friction. And if we look at this equation, we basically know everything except for n. We know AR, we know the mass, we know the angle, we know the coefficient of kinetic friction. We don't know the normal force. We do know the weight because we know the mass, and we don't know the normal force. So the only unknown is n. We can solve it from this equation. So I have mass times acceleration on the right-hand side. I add the weight times sine 30 to the right-hand side, where we calculate weight as m times g. Acceleration due to gravity, approximately 9.81 meters per second squared. And then we're left with n times cosine 30 minus n times mu k times sine 30. We factor out the n and divide through. We have cosine 30 minus mu k sine 30. If we punch in all of the numbers that we have up here, we get that the normal force is approximately 17.04 newtons. So that was one of the forces we were asked to find. The friction force we can then find almost immediately because we know the friction force is equal to the normal force times mu k. So if we plug that into our calculators, we get that the friction force is approximately 7.5 newtons. The last force, the force F of the arm pushing on the particle, is entirely in the transverse direction. And so we can get that from the transverse component of Newton's second law. So we have the sum of the forces in the transverse direction equals mass times the acceleration in the transverse direction. So F is in the transverse direction. It's in the positive transverse direction. The weight and the friction force have components in the transverse direction. In the negative transverse direction, they're both the side adjacent to the 30 degrees, so we'll use cosine. So minus the weight times cosine 30 minus the friction force cosine 30. And then the normal force also has a component in the transverse direction. If we look at the triangle, it's also in the negative transverse direction. In this case, it's the side opposite the 30 degrees, so we'll use sine. That's equal to mass times the transverse component of acceleration. Again, well, we know what the friction force is, or you could rewrite it as mu kn. We know the normal force. We know the weight is m times g. We know m. We know the acceleration. So the only force that we don't know is the force of the arm pushing on the particle F. And we can find that simply by moving everything else to the right-hand side of the equation. We have ma theta plus mg cosine 30 plus the friction force times cosine 30 plus the normal force times sine 30. We have all of those values. We plug them into our calculator. We get that the force of the arm is approximately 34.09 newtons. That was the last thing we were asked to find, and that concludes this example.